Alright guys, this is just the second part of the same PowerPoint that is linked to today about reaction favorability, and it just digs a little deeper. Now that we understand what entropy is, now we can really talk about whether a reaction will be favorable or not. So how can we determine if a reaction will occur without outside intervention or be favorable? Okay, remember, everything in the universe just wants to be stable. So how can we create a more stable universe? And remember guys, the universe isn't like the solar system and all the planets and stuff. The universe is just a system and the surroundings. Okay, I mean, it is true, everything in the universe also wants to be stable, but for what we're talking about, it's just the system and its surroundings. Okay, these are the requirements for a reaction to be a stable universe, to create a stable universe. If it has low enthalpy, right, so probably a negative delta H, and higher entropy, so a positive delta S. Low enthalpy, high entropy. Negative delta H, positive delta S. Okay? So if you have low enthalpy, you have an exothermic reaction where you have heat lost from the system. And the reason that that creates a higher entropy in the universe is because the surroundings gain that heat, which increases that particle disorder, right, which is entropy. So we need to talk about free energy in order to decide if something is going to be a favorable reaction or not. Okay, it's the ability to do work. Okay, the free energy of a chemical reaction. Delta G is the free energy change. Okay, and that's after a guy named Gibbs. That's where the G comes from. Okay, and the formula to calculate delta G is delta H, so the enthalpy, minus the temperature times the change in entropy, or delta S. Okay, so we're just going to have to tell you the enthalpy, the temperature, and the entropy, and you just plug them into this really simple formula. Okay, if your Gibbs free energy, or delta G, comes out to be negative, then the reaction is favorable. Okay, and you can kind of remember that because we've already talked about a negative delta H, or exothermic reactions, typically being your favorable reactions anyway. Okay, if your delta G, Gibbs free energy, comes out to be positive, it's going to be a non-favorable reaction. You're going to put in a lot of energy for that reaction to happen. It won't be a favorable, happen on its own type of thing. Okay. So this is a little table, and this is in the PowerPoint. I just wrote it down. If you prefer to memorize things, like if you just process things better when you have kind of a system memorized, then this is for you. If you do not like to memorize, if you would rather either understand what's going on or do some calculations, then don't worry about this. But it might be nice to just write down anyway. Okay? If your delta H is either positive or negative, compared with your entropy being positive or negative, it kind of tells you a rule of thumb for your Gibbs free energy and whether that reaction will be favorable or not. So if you want to write this down, pause the video and jot it down, but I'm not going to just read it off to you. Okay, so let's do a quick sample problem using that Gibbs free energy formula, which remember is delta G equals the enthalpy minus temperature times entropy. Okay. A reaction has an enthalpy, or a delta H, of negative 28.8 kilojoules. You can't have kilojoules, right? All of our constants are in joules. So we're going to make that negative 28,800 joules. And an entropy of negative 54 joules per Kelvin. Is it favorable at 298 Kelvin? So there's my temperature, there's my delta S. You're just plugging them in, right? Enthalpy minus the temperature times entropy. And when you plug all that in, you get a Gibbs free energy of negative 12,700 joules, which means it's favorable. If you get a negative delta G, it's favorable. Okay, so now I want you to try page 6, which is just that last page of your packet you've been working from this unit, number 6 through 21.